Hello, my name is Roshene McCool and I am a Senior Market and Technology Development Manager working at Corning Optical Fibre and Cable. Today I'm going to talk to you about high capacity pathways and the fibre innovations that enable those high capacity pathways for a connected future. So high capacity pathways will support the multi-service networks of the future. As connected as we think we are today, the reality is that very few people in the world have a fibre connection to their home. Even in places like the EU27, only 20% of homes have a fibre connection directly to their home. And in most places of the world, we don't even see a copper connection, an ADSL or a VDSL connection or a CATV copper connection into the home. And so we really need to connect more people in this connected world. To connect more people, first we need more fibre pathways. And to serve those fibre pathways, we need more capacity within the network. And so in this presentation, what I'm going to do is I'm going to explore how fibre-based space division multiplexing can support both pathway and capacity expansion in the future. So why do we need more pathways? Well, we need more pathways to serve the increase in mobile subscriptions that we expect. There is a prediction that we'll see a rise in 800 million mobile subscriptions worldwide by 2024. And whilst to the user that mobile service might be wireless, actually within the core of those mobile networks, they're very fibre connected systems. We need more pathways to serve more users who have a requirement for higher bandwidth to the home and to the business. And so we expect to see more fibre connected homes and businesses, and indeed a rise of 200 million subscribers worldwide by 2024. We need more pathways to connect the IoT devices that sit within our homes and within the network, communicating with that network, with each other and with data centers to provide information about the world around us. And indeed, we expect to see a rise of 10 billion IoT devices worldwide by 2024. We need more pathways to connect the rising data center locations. As we see data centers regionalize, we expect to see more data center locations. And indeed, that's happening today, and we expect it to continue in the future. So why do we need more capacity? Well, we need more capacity because more of us are working remotely. There's been a 4.7 times rise since the start of the pandemic of remote workers. And we're using more video to communicate. Video calls are the second most important way of connecting friends and family after voice calls. And it's the quality of that video call that determines a user's assessment of the quality of their service. We're not just seeing this rise in video and the capacity demands that requires on the user side. We see carriers who are reporting a 50% rise in symmetrical demand since the start of the pandemic. And what that means is we need capacity both downstream and upstream. Fibre is an ideal medium for symmetric services because it's a broadband medium. Easily upgraded to these kind of symmetric services compared to, say, the legacy copper systems that have been serving asymmetrical systems to the home for some time. So now let's start by looking at pathways. At the most basic level, optical cabling has already evolved to support optical pathways by delivering cables with high fiber counts. In the late 1990s, a very high fiber count cable might have been a 96 fiber cable. But today, 288 fiber, 864 fiber is a common fiber count in cables. And indeed, we've seen cables with fiber counts up to 3,546 fibers and beyond. Because of the limitations in the duct space in the network, whilst we increase the fiber count, the space within the network isn't increasing. And that means that we've started to see a focus on density of fiber in cables because we need more fiber pathways, but we can't make those cables just infinitely bigger. We have to fit them within the space available within the network. And so as we see higher fiber and cable density, the fibers have evolved in order to enable that. So a legacy fiber had a 242 micron outer diameter before colouring. And we've seen fibers with lower outer diameter, around 200 micron or 190 micron, in order to reduce the cross-sectional area of the fiber within the cable and increase the density of fiber within the cable. Corning Smf28 Contour fiber was recently launched, and that's a brand new fiber which has been specifically designed to give more pathways within the network with attributes that support efficient network installation and operation. This SMF28 Contour fiber is available in a legacy 242 micron outer diameter or a 190 micron outer diameter. And that lower OD option has been designed specifically for higher density cables. The lower OD delivers a 40% cross reduction, a 40% reduction in cross-sectional area compared to traditional fibers. But importantly, it retains that 125 micron cladding diameter for splicing compatibility. SMF28 Contour fiber retains the 9.2 micron mode field diameter, which means it's compatible with most of the existing legacy fiber in the network. And that means that it can be easily spliced in comparison to fibers that have a mismatch with their mode field diameters. That increase in splice yields compared to fibers with incompatible mode field diameters means time saved in remedial work to fix splice errors or ambiguous test results that are a feature of fibers, splices between fibers that have different mode field diameters. So now let's think about capacity. So on the slide here, what you can see is the capacity equation. That capacity equation is governed by Shannon's law, which is made up of two components. The first is a linear component, and that's to do with the spectral bandwidth of the fiber, which is B here, and also the number of pathways, which would be the number of fibers within the network. It has a second piece, which is a logarithmic piece of this equation, and that's associated with the signal to noise ratio. Now, until about 2 to 3 years ago, when space division multiplexing came into focus, it was an improvement in that SNR value within that equation, which was the main focus for optical fiber networks, with some focus on spectrum. But today, space division multiplexing and the available spectrum within each of the fibers within those networks has become a focus. And in this presentation, I'm going to focus particularly on this linear piece, which is about the bandwidth available within the fibre and the number of fibres that we can put within a route in the network. The low attenuation passband of silica fibres goes from about 1260 to about 1675 nanometers. And that passband is broken up into windows. So we have the O band, the E band, the S band, the C band, the L band, and the U band. Traditionally, long reach and medium reach systems have used the C band. This is the passband also of optical amplifiers. And so for any system that needed amplification along the route, the C band has been the preferred choice. It's also where dominantly dense WDM systems have been used. In short reach systems, that has used mainly the O band. That's the low dispersion part of the fibre transmission. Some systems like GPON have used the S band for the upstream signals, and the U band has been used for monitoring and testing purposes within the network. But increasingly what we see is in order to increase the amount of bandwidth over these systems, long reach systems are going from the C band moving into both the C and the L band. And short reach systems are using much more of the O band spectrum, and indeed new systems like SGS PON, NG PON2, and WDM systems in the C and L band. So even in short reach, we're now seeing systems that are utilising the C and L band to get that extra bandwidth and allow for coexistence of many systems within the network. Fibres have evolved to deliver this low loss wide bandwidth signal transmission. Corning's brand new SMF28 Contour fibre is a wide band fibre. It has a low water peak, so it's low loss right across the bandwidth of the fibre. And it's also bend protected, which becomes important if we are transmitting in the C and L bands, which are particularly affected by bend. So SMF28 Contour fibre has an industry-leading low loss for fibre of its type, and that low loss is bend protected with an ITU-T G657A2 bend specification. And what that means is that that fibre can experience bends down to a minimum bend radius of 7.5 millimetres without significant loss of signal. So what about the future? I've shown how advanced fibres like SMF28 Contour exist today to support the construction of future networks. But to go beyond 6,912 fibre cores in a cable, or to make those cables even smaller to fit within the space available in the network, we may need to transform and go for a revolutionary change within the fibres in those cables. And that revolutionary change may include reducing the actual glass within the fibre. So reducing that glass clad from 125 micron that we're very familiar with today, potentially reducing that even further to get smaller fibres, or maybe having many pathways within a single fibre, like with multi-core fibre. Now, these fibre designs are considered revolutionary because for both of these fibres, we're going to need a change in the ecosystem for splicing and connectorization. Those systems will need to adapt and change. The reward for that will be more pathways within the network, and we've described why future networks may need more pathways. And if we can overcome that development and ecosystem challenge, then these kinds of fibres could support an expansion in pathways within the network in the future. So I hope I've shown how high capacity pathways will support multi-service networks of the future. And we can deliver advanced fibres today to deliver those pathways, but fibre innovation will continue, and we're likely to see advanced fibres in the future. So thank you very much.